Hello there, and welcome to Fall Asleep to Astronomy. I'm so glad you could join us in this quiet, shared moment. Wherever you are, allow the edges of your day to soften and your thoughts to grow dim, like the distant light of a slow-turning star. The cosmos is patient, and tonight, we turn our gaze toward a story the universe has been holding for a very long time. Imagine we are sitting quietly in the NASA archives, letting starlight fall across old, forgotten blueprints. We're searching for the story of 3IATLAS, a mysterious wanderer whose passing was so swift it barely left a trace. There are things we've been told, and then there are the whispered truths hidden between the data points. Tonight, we'll move beyond the headlines and simply listen to what NASA should have told you about this quiet comet. If these gentle journeys bring you comfort or settle your mind, a soft like and a quiet subscribe help others find their way here too. For now, let the darkness hold you and the starlight guide us. When you're ready, we'll begin this gentle exploration together. You might have known that 3IATLAS has just slipped past our sun, brushing by that bright heart of our system in a path that looks simple on paper, but feels anything but simple in the imagination. This close encounter has peeled back a little more of its disguise and shown us details we'd never seen before. And somehow, every new fact only makes its true nature feel more mysterious. If this wanderer is really a comet, then it keeps refusing to behave the way comets are supposed to behave. And if it is not a comet at all, if it is something we do not yet have a neat label for, then the whole world is about to find that out. Because 3IATLAS is not just passing through the outskirts, it is coming inward, toward us, moving through the sun's domain in our direction. There is a quiet, almost eerie timing to its arrival. Of all the years it could have chosen to sweep through our neighborhood, it has come now, in 2025, during a time when our own star is at its most restless. The sun goes through long, slow cycles of calm and agitation, like a giant light that sometimes steadies and sometimes flickers. About every 11 years, it reaches a kind of fever pitch that astronomers call the solar maximum. For most of that cycle, the surface looks relatively smooth, with only a few dark sunspots and short-lived outbursts. But as solar maximum approaches, the calm phrase, magnetic fields twist and knot beneath the surface. Dark spots bloom and multiply. Bright regions flare like sudden sparks on a campfire log. We are living in that heightened moment right now. Around the time this interstellar visitor began to curve in toward the inner solar system, our star was already building toward this peak. The latest solar maximum began in October of 2024, and, like a stormy season, it tends to last for roughly a year. During that stretch, the sun's face is stirred into constant motion. Huge arcs of charged particles leap out from its surface. Loops of plasma gas so hot its atoms have been stripped apart, rise and fall in towering shapes many times taller than Earth. The sun throws off sudden flashes of X-rays and ultraviolet light that wash through the solar system at the speed of light, and, slower but more tangible, great gusts of material that take days to arrive. Those bigger outbursts are called coronal mass ejections, immense bubbles and clouds of the sun's outer atmosphere that are flung into space when its magnetic fields snap and realign. You can picture them, if you like, as bright fragments of the sun's own skin, pushed away from the star and set adrift along the invisible wind that streams outward in every direction. Most of them wander into the emptiness between the planets and fade, but some of them happen to line up with Earth. When that happens, we feel the sun's unrest in a much more intimate way. Over the course of 2025, people all across the high latitudes have stepped out into the night and found the sky painted in colors they are not used to seeing. Greens and purples, curtains and bands, ripples and pillars, all moving in slow, silent waves across the darkness. These are the auroras, the northern and southern lights, glowing where the stream of charged particles from the sun runs into our planet's magnetic field and upper atmosphere. Those lights are not just a show. They are the visible sign that pieces of the sun have traveled all the way here, brushed against the thin shell of air that protects us, and been turned into color. Some nights, cameras pick up auroras much farther south than usual, spreading into skies that rarely see them. Someone might step outside to take out the trash or walk a dog and look up, expecting ordinary stars, only to find the whole horizon softly veiled in shifting light. They may not know the words solar maximum or coronal mass ejection, but they are watching those processes play out above their own rooftop, written in emerald and rose. It is the sun reaching across space and touching our world with a gentle, glowing hand. It is a strange, comforting thought while you stand on the ground, bundled in a jacket somewhere under the northern sky. Light and particles born on the surface of the sun are colliding with atoms high above you, making the night itself shimmer. That same restless activity is what 3IATLAS is flying through now. The solar maximum is not some quiet, abstract number in a scientist's notebook. It is a season of storms, and our visitor has arrived right in the middle of it. As we ease past the peak of this restless phase, the sun is still more active than usual. The most intense flares and outbursts may be behind us, but the surface remains busy, patterned with complex magnetic regions and flares that erupt without much warning. This is the environment into which 3IATLAS has glided, threading its way through the sun's light and wind. The timing means that our instruments, our satellites, and our observatories have been watching space more carefully than usual, alert for bursts of radiation and streams of particles. In a way, the sun's own turbulence has made us more attentive, more ready to notice an object like this and follow it closely. For any comet, whether it was born in the deep cold of our own system or set loose long ago around some other distant star, the most dramatic chapter of its life is when it swings in close to a star. That close approach has a special name, perihelion, from words that mean near the Sunday. On star charts, it is just a point along an orbit, a minimum distance written in neat digits. In reality, it is the moment when the quiet, frozen surface of a wandering object meets the full intensity of a star's energy. As 3IATLAS passed through perihelion, it would have been bathed in more light and heat than at any other time in its long journey between the stars. The gentle, steady sunlight that barely touched it in interstellar space has become a fierce flood. Radiation beats down on its surface. The solar wind, a constant stream of charged particles, presses against it, and riding on top of that wind, sometimes in smooth flows and sometimes in great, gusty blasts, are the coronal mass ejections thrown off during this solar maximum. The very same kinds of storms that cause the auroras to dance above Earth are sweeping past 3IATLAS as well, stirring whatever materials lie at or near its surface. If 3IATLAS is a comet, this is the point at which its ices should begin to wake up. Substances that were frozen solid in the cold between the stars start to sublimate, turning directly from ice into gas. Jets of vapor and dust could stream away, forming a halo or coma around the nucleus and eventually stretching into one or more tails that point away from the Sunday. For astronomers, watching that change is like watching someone slowly open their hand. The way the coma grows, the way the tail brightens or bends in the solar wind, the colors hidden in the light it reflects, all of these are quiet clues to what 3IATLAS is made of and how it responds to the star it is passing. If it is something else, something more rocky or metallic, the reaction to this flood of energy will be different, subtler, perhaps, but still there in the way sunlight reflects from its surface and in the way it responds to the push of the solar wind. A rocky body might darken or brighten in unexpected ways, or show almost no tail at all. A more metallic object might reflect light sharply, or conduct heat in a way that changes how quickly it warms and cools. These are delicate differences, easy to miss when an object is far away and faint, but around perihelion, they become just a little easier to measure. Before this close pass, 3IATLAS was little more than a faint point of light in our telescopes, a small moving speck against a crowded background of stars. It was so far away and so dim that even our best instruments had trouble teasing out details. Astronomers could track its path and measure how its brightness changed, but actually seeing its shape, its structure, or the fine features of any tail or halo was almost impossible from Earth. Most of the time, the data arrived as thin lines on a screen, numbers in a table, patterns that only gradually turned into a picture in the mind. That began to change as it drew nearer, and other spacecraft, scattered through the solar system, were brought into the effort. Telescopes in Earth orbit joined those on the ground. Probes circling other worlds were asked, very quietly, to turn and look. Earlier this week, NASA released a new image that feels like a small gift from this passing stranger. It is the highest resolution photograph of 3IATLAS that we will ever have, captured at a unique moment and from a unique vantage point, a satellite orbiting Mars. Watching as the interstellar object swept past at the closest distance it will ever come to any planet. From that perch above the red planet, the spacecraft could see 3IATLAS in a way no Earth-bound telescope ever could. The gap between observer and object was smaller, the intervening haze of our own atmosphere was gone, and the angle of the sun's light painted its features in sharper relief. What the image shows is still delicate, still limited by distance and size, but it is more than a speck now. It is a real object with a discernible form, a body moving through the shared light of the Sun and Mars and Earth. Somewhere in a quiet control room, far from the deserts of Mars and the cold track of 3IATLAS, a handful of engineers and scientists would have watched that image appear on their screens for the first time. For them, it is the result of years of planning, careful commands sent across millions of kilometers, and instruments kept alive in the harshness of space. For the rest of us, it is a single still frame that says, "This is what an interstellar visitor looks like when it passes close to our family of planets. This is the face it shows us in the brief time we share." Knowing that this is the closest 3IATLAS will ever pass to any world in our system gives the picture a kind of softness and weight at the same time. This is our single best look, our one clear glimpse before it continues on, and the details blur again into a dim point among countless others. We do not have a fleet of spacecraft ready to chase it down, no quick way to send a probe to match its speed and fly at its side. All we can do is aim the eyes. We already have telescopes, satellites, cameras orbiting other worlds, and gather as much light as possible while it is near. The satellite around Mars caught it in that brief window, in that narrow slice of time when an interstellar traveler and a human-made machine happened to cross paths under the same star. For a moment, their stories touched. A visitor from another system, shaped by a different sun long ago, and a small craft built by hands on Earth, both illuminated by the same golden light, both moving through the same shared space. When that long-awaited image from Mars finally arrived, a lot of people quietly hoped it would be the moment everything clicked. Maybe the shape would stand out just enough, or a tail would appear with some strange structure that gave away what 3IATLAS really was. After all the careful tracking, all the excitement about an interstellar visitor passing so close to a planet with a camera in orbit, there was a small, shared wish that this would be the picture that turned mystery into clarity. But when the data settled into place and the image sharpened, what appeared was a soft, blurry glow. In the frame, 3IATLAS looked like a big, fuzzy white dot, slightly brighter than the background, slightly more defined if you stared long enough, but still simple, almost shy. No sleek contours, no obvious fragments, no dramatic, sweeping tail full of intricate detail, just a luminous smudge against the darkness. It wasn't a bad image. In a technical sense, it was wonderful. Our best, sharpest look at an object born around some other star, captured from another world. But to the human eye, to that quiet part of us, hoping for something cinematic, it could feel a little underwhelming. No big secret revealed, no sudden aha moment, just a dot that refused to tell us exactly what it was made of, or how it had been built by its distant home system. Still, even that soft dot had meaning. It told us how compact the object seemed, how the light spread out from its core, how the surrounding haze behaved. It confirmed that the coma, the cloud of gas and dust around it, was real and substantial. But if we wanted something more dramatic, something that changed not just how clearly we saw 3IATLAS, but how we understood it, the real story was happening somewhere our eyes could not follow directly, right next to the Sunday. You might have heard that when 3IATLAS was at its closest point to the Sun, we couldn't actually see that passage from Earth. Our planet was on the wrong side of the solar system, tucked away so that the Sun itself lay between us and the object. From our vantage point, the scene was blocked by that blinding disk of light. In a simple diagram of the orbits, it almost looks like a cosmic game of hide and seek, the visitor slipping behind the Sun from our line of sight, just when things were getting most interesting. In a broad sense, that's true. If you were standing on Earth, or looking through even the most powerful ground-based telescope, there was no way to peer straight past the Sun and watch 3IATLAS skim through perihelion. The glare is overwhelming, but orbiting high above our planet, there are a couple of instruments that are built to stare at the Sun in a very different way, and they gave us a narrow but precious window into what happened next. 2 satellites, one American, one European, carry special kinds of telescopes whose entire purpose is to look at the region around the Sun rather than the Sun's bright face itself. The idea is deceptively simple. Imagine holding a small coin at arm's length to block out the Sun in the daytime sky so you can see the faint halo around it. A coronagraph works on the same principle, but with careful precision. Inside the telescope, there's a small disk placed exactly in line with the image of the Sun's surface. That disk acts like an artificial eclipse, covering the dazzling central light and revealing the Sun's outer atmosphere, the corona, which is normally lost in the glare. With that central brightness masked, the instruments can pick up delicate structures in the corona, looping arcs of hot plasma, wisps of outflowing gas, and the wide expanding shapes of coronal mass ejections. It's like dimming the brightest light in a room, so your eyes can finally adjust and notice the soft glow in the corners. These space-based coronagraphs let us watch the sun's weather unfold in real time, its storms, its flares, its shock waves rolling out through space. They also have a quiet extra gift. Anything that happens to pass near the sun from our perspective, but is not the sun, can appear in those images too. Comets, asteroids, bits of spacecraft hardware, interstellar visitors, if they wander into that glowing field around the artificially blocked disk, they show up as small moving lights, traced across the frames as they approach, swing around, and depart. The American GOES satellite system and the European SOHO spacecraft both carry coronagraphs like this, always watching, always recording the sun's activity. When 3IATLAS made its close pass, those instruments were ready. Even though Earth itself was hidden on the far side, these satellites, floating in space, had the perfect vantage point to see the visitor's glow change as it moved through perihelion. The first sign that something unusual was happening came in the simplest form, a change in brightness. As 3IATLAS drew nearer to the sun, the little point of light in the coronagraph images began to intensify. At first, this was expected. Any object moving closer to a star will reflect more light. The sun's rays arrive more densely, the surface warms, ices and dust become more active, and the object looks brighter to a camera. That's just the ordinary geometry of light and distance. But this time, the increase was not gentle. Over a span of just a few days, the brightness of 3IATLAS didn't just creep up, it surged. By the time it was nearest the sun, it had become roughly 400 times brighter than it had been shortly before. Try to imagine a single star in the sky suddenly shining not twice as bright, not 10 times, but hundreds of times more luminous, all in the space of a very short interval. That is the kind of change we are talking about. For a typical comet, an increase in brightness of 10 to 100 times as it swings past the sun would already be impressive. The exact amount depends on how close it gets, how much ice it's carrying, and how easily that ice turns into gas. When sunlight heats the surface, those ices sublimate, carrying dust along with them, and the cloud around the nucleus swells. The comet's coma and tails catch more and more light, and from our perspective, it brightens. But even in that context, what 3IATLAS did stands out. A 400-fold rise is not just on the high end of normal, it pushes beyond what we are used to seeing at all. That dramatic increase hinted that something about 3IATLAS, its composition, its structure, or the way its surface responds to heat, might be very different from the comets we've studied closer to home. It was as if the object had been whispering along at a modest glow and then, upon nearing the sun, burst into a sudden, intense whisper of light, loud enough in the data to make everyone sit up a little straighter. Brightness is only part of the story. Light has another subtle way of speaking, and that is through color. Not color in the sense of a bold, obvious hue you would see with your naked eyes, but in the more delicate sense of which wavelengths are a little stronger than others when the light is split and examined. By looking at the spectrum of light reflected or emitted by an object, astronomers get clues about the materials that are present there, the gases, the dust, the molecules that glow or reflect in particular shades. When 3IATLAS was first observed months earlier, back in the softer days of summer, most of the light we picked up from it leaned toward the red end of the spectrum. That doesn't necessarily mean that if you could have flown out and looked at it with ordinary eyes, you'd see a bright ruby comet hanging in space. It's subtler than that. It simply means that, measured carefully, the balance of wavelengths was tipped in favor of redder light compared to other colors. That, in itself, was not strange. Many comets wear a reddish tint in their scattered light. Their comas, those hazy envelopes of gas and dust surrounding the solid nucleus, contain fine particles and molecules that are good at reflecting or emitting red light. Dust grains, organic materials, and various gases all contribute to that warm tilt in the spectrum. So when 3IATLAS showed up as a mostly red object in those early observations, it felt almost reassuring. For all its peculiarities, at least this one feature made sense. We knew from other measurements that 3IATLAS did have a coma. The light around it wasn't coming only from a bare, rocky core. There was gas and dust spread out in a cloud, responding to sunlight. That fitted neatly into the picture of a comet-like body, an icy, dusty nucleus wrapped in its own breath of vapor, trailing material behind it as it moved. The red leaning light was one of the few, quietly normal things about this very abnormal traveler. And then, something changed. In early September, as the object continued its journey and more data came in, astronomers noticed that the light from 3IATLAS was no longer leaning so heavily into red. Instead, its spectrum shifted toward green again. This doesn't mean it would have looked like an emerald jewel if you'd glanced at it through a backyard telescope, but in the careful measurements, the balance of color had moved. Green had begun to dominate. Comets can sometimes glow green for familiar reasons. Certain molecules, when excited by sunlight, like diatomic carbon or cyanogen, can emit a greenish light in the coma. We've seen that kind of glow in other comets before. But in the case of 3IATLAS, the timing and the exact way the color changed did not line up neatly with an easy, familiar story. It had started out looking red in the spectrum, comfortably in line with dusty comets, and then shifted into this greener state in a way that left scientists scratching their heads. By the time the change was clear and confirmed, it was obvious that something unusual was going on. And yet the why remained out of reach. Maybe it was a particular mixture of ices under the surface, waking up in stages as the object warmed. Maybe there were layers, with different gases released at different distances from the sunday. Maybe the object's surface had been altered by its long voyage through interstellar space in ways we don't fully understand. For now, those were all just quiet guesses. The simple truth was that 3IATLAS had mysteriously turned green, and no one could say with confidence exactly what triggered that transformation. You might think that would be enough surprises for one visit, an interstellar object with an extreme brightening and a puzzling shift from red to green. But as perihelion drew nearer, and the coronagraphs watched it bathe in the sun's full intensity, 3IATLAS added one more layer to its changing face. While it was moving through the crowded light near the sun, the spectrum of its glow shifted yet again. The green that had puzzled observers began to give way, and the light from 3IATLAS drifted toward blue. In the images and data, it took on a bluer character than before, another step away from the red-leaning signature it had worn in the beginning. That, too, is strange. Natural comets that we followed closely usually become more reddish as they come closer to the sunday. The increased heat releases more dust, and the dust tends to scatter sunlight in a way that enhances the red component. More dust, more warmth, more red in the mix, like a faint, rusty filter deepening as they near the star. Seeing an object move instead from red to green to blue as it approached perihelion runs against that familiar pattern. It's as though 3IATLAS is walking backward through the usual sequence, changing its colors in a direction that feels quietly upside down compared to what we expect. If you imagine laying out all the colors of light in a smooth line, like a soft ribbon spread across a table, red would be at one end and blue at the other. Somewhere in the middle, between the warm glow of red and the cool calm of blue, you'd find green. That's what astronomers mean by the spectrum, a gentle gradient of colors, each tied to a different wavelength of light. So when we say that 3IATLAS first leaned red, then shifted to green, and finally moved toward blue, we're not just shuffling labels. To go from red to blue, the light doesn't simply slide along a short distance. It has to travel across that whole range of colors, passing through the middle. Green is the stopover point, the halfway house. If you were expecting a comet to get redder as it warms, moving farther into the red corner of this ribbon, then seeing it journey the other way, through green and out toward blue, is like watching someone calmly walk out the door you were sure they were about to enter. When we take that strange journey in color and place it beside the enormous jump in brightness, the 400-fold surge as it neared the sun, we end up with a puzzle that doesn't have many simple, natural answers. Both things together, the brightening and the bluing, are like two voices in a choir singing the same odd note. You can't help but listen more closely. One possible explanation, if we stay with what nature can reasonably do, is that 3IATLAS suddenly began releasing a fresh, massive cloud of gas that happens to shine more brightly in blue light. In that picture, something in or on the object woke up as it was heated, some new layer of ice or trapped material, and began to vent in great quantities. The gas would spread around the object, become part of the coma, and scatter or emit light in that bluer part of the spectrum, tipping the overall color away from green and toward blue. We don't yet know exactly what kind of gas that would be. It isn't one of the familiar cometary culprits we usually see dominating the blue part of the spectrum, at least not in the usual way. The pattern doesn't quite match our standard stories. But that doesn't immediately make it unnatural. Space is full of combinations we haven't cataloged yet, mixtures of ices and molecules that formed under different conditions around other stars. An interstellar visitor might easily carry something that is rare or absent in our own local comets. So in that first quiet explanation, you can imagine 3IATLAS as a layered body, like a frozen onion with shells of different materials laid down over time. Far out in the cold, only the most volatile ices might escape, giving it that early red-leaning glow. As it moved inward and warmed more deeply, another layer might begin to vent, rich in gases that favor green. Closer still, yet another composition might be exposed, producing a sudden rush of material that shines blue. It's a gentle, gradual picture of chemistry, unfolding with temperature, each step revealing a different face to the sunlight. The second natural explanation is a little more dramatic, but still firmly in the realm of familiar comet behavior. Maybe what we're seeing is not just gas waking up, but the first stages of a breakup. When a comet passes close to a star, the stress on it can be enormous. Heat seeps in and out unevenly, ices expand and escape, jets fire off in different directions, and old structural weaknesses can finally give way. Some comets simply come apart under that strain, cracking into smaller pieces or even disintegrating into a cloud of fragments and dust. If 3IATLAS were breaking up, the sudden brightening could come from the fresh surfaces revealed as it fractures. When a comet splits, material that was once buried deep inside cleaner ice, more pristine dust, gets thrown into space. Those new surfaces and particles can reflect and emit a lot more light than the older, weathered crust. The color could change too, depending on what those inner layers contain. A breakup event, starting subtly, might show up in our instruments as a dramatic rise in brightness, a shift in the way light is scattered, and a change in the spectrum. Comet breakups are not rare tragedies in the sky. They are almost a kind of tradition. Many comets that pass close to the sun end up torn apart by tides and heat and their own escaping gases. We've watched them split into chains of glowing fragments, their tails tangled and stretched, their comas swelling as they fall to pieces. So it would not be strange, in principle, to say, 3IATLAS must be doing the same thing. But in this particular case, that explanation runs into a simple problem. We've already seen 3IATLAS emerge from its passage around the sun, still in one piece. It came out the other side of perihelion intact, still behaving like a single, cohesive object rather than a cloud of debris. Whatever else it did in that bright, crowded space near the star, it did not fully shatter. There may have been stress, maybe small changes we haven't yet mapped, but not the kind of dramatic disintegration that would cleanly explain the blue flash as the start of its destruction. So we're left in an in-between place. A sudden surge in brightness, an unusual journey through the spectrum from red to green to blue, and an object that seems to have survived its close pass without obvious fragmentation. The natural explanations are not gone, but they sit a little uncomfortably. They can fit parts of the story, but not all of it, without some stretching. At that point, the human imagination does what it has always done. In the face of partial knowledge, it drifts a little further, edging toward the speculative, with a half smile and a hint of self-awareness. People start to joke about tinfoil hats and alien engines. The idea isn't new. Ever since Oumuamua, the first known interstellar visitor, showed some odd motions and shapes, there has been a small chorus of voices, wondering if any of these objects might be artifacts rather than accidents, machines, instead of mountains of ice and rock. If there were one thing in 3IATLAS's behavior that would tempt someone down that path, it would be this combination of light and motion. Because the color change and brightening do not seem to be fully explained by the sun's influence alone, the thought arises, what if some of that change came from within? From activity that is not just ice sublimating, but something more deliberate? It remains far more likely that we are dealing with unfamiliar ices and complex chemistry, but the mind can't help glancing, just for a moment, at the more exotic possibilities. There is a reason that particular idea catches hold. Right after the bright blue phase, 3IATLAS does something that, at least on paper, looks like the kind of behavior you'd expect from an object under its own power. It changes course, not in the simple, predictable way you'd get from gravity alone, but with a subtler twist. As it moved through perihelion, observers noted that 3IATLAS began to experience what astronomers call non-gravitational acceleration. It's a technical phrase, but the core idea is gentle enough. The object's motion started to include changes that could not be accounted for by the pull of gravity from the sun and the known planets. In other words, it wasn't just falling along the path that gravity would assign to a passive, unpowered stone. Something else was nudging it. When we say acceleration, we're not necessarily talking about a dramatic, science fiction jump, no sudden darting across the sky. These are often tiny shifts, small deviations that only become obvious when you compare precise measurements over time. But even a delicate nudge is telling. Gravity, we understand well. We can calculate the path an object will take under its influence with great accuracy. If the object moves differently than that prediction, the difference must come from another force, some push or pull layered on top of gravity's steady hand. Non-gravitational acceleration, often shortened to NGA, simply means that an object's motion includes contributions from those other forces. The direction of that extra push doesn't really matter from the definition's point of view. It could make the object move faster or slower along its path, or drift a little sideways, or curve in a way that pure gravity wouldn't demand. Up, down, diagonal, any direction is allowed, as long as the change can't be explained by gravity alone. For something like a spacecraft, NGA is expected, even desired. Engines firing, gas venting, solar sails catching light. All of these can create non-gravitational accelerations. For a natural object, the situation is more subtle, but not mysterious. Comets, especially, are famous for it. A comet is not a solid, inert stone. It is more like a leaky snowball, constantly venting gas and dust as it warms near a star. Jets of vapor burst from its surface, sometimes in uneven patterns, like little thrusters that are turned on and off, not by conscious choice, but by the rhythm of sunlight and the shape of the nucleus. Each jet carries momentum. When gas rushes away in one direction, it gently pushes the comet in the opposite direction, just as air escaping from a balloon can send the balloon skittering across a room. All those tiny pushes add up. From a distance, tracking the comet's motion, you might notice that it's not following exactly the path that gravity alone would dictate. It speeds up a little here, slows down a little there, drifts slightly off the curve you'd draw for a simple, silent rock. That is non-gravitational acceleration too. In that sense, a comet's coma and jets are like a soft, natural engine, one that doesn't have a pilot, but still alters the course in ways we can measure. So, in that regard, an object like 3IATLAS feeling NGA as it sweeps around the sun is not, by itself, strange at all. If it is a comet, it is wrapped in a glowing cloud of gas and dust, and that material is constantly being thrown outward. It makes perfect sense that these escaping gases would tug and nudge at the nucleus, shifting its motion little by little. We would, in fact, expect some amount of non-gravitational acceleration during perihelion, simply because the coma is active and the jets do not cancel each other out perfectly. The sun heats the surface, the ices respond, and the object gets gently pushed around by its own breath, even as gravity does the heavy lifting of curving its overall path. For a natural comet, a little bit of non-gravitational acceleration is like a bit of background noise, expected, gentle, always there in some small way. Gas escapes. The nucleus gets nudged. The path wobbles a little. It fits. It feels right. But with 3IATLAS, the familiar pattern doesn't show up when you expect it to. For almost all the time we watched it crossing the solar system on its inward journey, there was essentially no sign of that extra push. Measurement after measurement showed the same thing. Its path was clean, almost eerily straight, like a stone gliding along a perfectly calculated line. That kind of steadiness is unusual for a comet. Most cometary orbits, when seen up close, have tiny imperfections, little bends and shifts, as jets of gas push this way and that. The more active the coma becomes, the more those tiny pushes add up, and the comet's track starts to look a little like handwriting instead of a ruler's line. As it gets closer to the sun, the outgassing grows stronger, more material blows away, and the wobbles become easier to spot. You almost expect it. The closer to perihelion, the more the comet fidgets under the combined influence of gravity and its own breath. 3IATLAS refused to do that. It sailed inward without those small, telltale jitters, holding a steady course as though nothing was venting from its surface at all. And then, right when it reached its closest point to the sun, everything changed, not gradually, but sharply. On October 29th, the day 3IATLAS passed nearest to the sun, observers saw a sudden deviation. The object's motion shifted in a way that could not be blamed on gravity alone. In the space of a single day, its path bent away from the sun by around 135 kilometers, and its motion along the sun-object line included an extra change of about 60 kilometers. Put together, those shifts give roughly 200 kilometers of non-gravitational acceleration per day, a kind of total extra motion that sat on top of what gravity was already doing. 200 kilometers a day might not sound dramatic in a life filled with thousands of kilometers and millions of miles as abstract numbers, but for an object moving under the precise control of gravity, it stands out. It's like watching a leaf drift down a river exactly as the current would carry it, and then, with no warning, seeing it start to veer sideways against the flow. You might not notice if you glanced once, but if you trace its path carefully, the difference is unmistakable. To understand how unusual this is, you can set 3IATLAS beside something similar, another interstellar comet. The object known as 2I, Borisov, is one of the only other visitors we've seen arriving from beyond our system on a clear, hyperbolic path. When astronomers studied its motion, they found signs of non-gravitational acceleration, two tiny jets of gas pushing it in ways gravity alone couldn't explain. But the amount was much smaller, on the order of about 100 kilometers per day. That's still interesting, but compared to 3IATLAS, it's modest. Borisov's NGA is about half of what we see in Atlas. And if you look at a classic, homegrown comet from our own system, the contrast grows even stronger. Hale-Bopp, one of the most famous comets of the late 20th century, was a large, active body that put on a spectacular show in Earth's sky. It had powerful outgassing, a bright nucleus, and long, beautiful tails. If any comet were going to show strong non-gravitational effects, you might expect Hale-Bopp to be near the front of the line. Yet Hale-Bopp's NGA was only about 1% of the value measured for 3IATLAS. In that light, what the Sun seems to have done to this interstellar visitor is remarkable. As it moved through perihelion, 3IATLAS became brighter than we expected, bluer than we expected, and more strongly nudged off its gravity-only course than any comet we've ever tracked. All three changes, light, color, and motion, rose to meet that moment in a way that feels quietly, insistently strange. And just when those numbers were still settling into notebooks and computer models, the images added another layer to the mystery. On November 8th, only a few days after its closest brush with the sun, a new photograph of 3IATLAS appeared. At first glance, it looked familiar in the way many comet pictures do. A bright core surrounded by a soft, luminous halo, drifting against the darkness. But if you lingered on it, the structure began to unfold. At the center, there was that glowing envelope, the coma wrapping around the nucleus like a hazy shell. Estimates put its reach at around 500,000 kilometers in every direction from the core, a vast cloud of gas and dust that the object had exhaled into space. That size alone is impressive. Imagine a ghostly sphere, many times larger than the distance from Earth to the Moon, all of it so thin that you could pass through it without feeling a thing. and yet bright enough to be seen from millions of kilometers away. Beyond that halo, though, the image showed more. Extending out from the coma were at least 7 distinct jets, narrow beams and fans of material shooting away from the heart of 3IATLAS into the surrounding space. They weren't just vague hints. They stood out as clear, separate streams, like the fingers of a hand stretched open. Most of those jets pointed in the direction you might expect, away from the sunday. That fits with the idea of sunlight driving gas out of the nucleus. The sun heats the surface, ices turn into vapor, and the flow of particles is carried outward, pushed along by light and the solar wind. It makes sense that, overall, the gas would be fleeing the star that is warming it, but not all of the jets were behaving that way. A couple of the smaller ones were angled toward the sun, as if some internal vents were releasing gas in directions that weren't simply away from the light. This mixture strong streams, mostly pointing outwards, with a few thin but clear jets pointing inward, gave the image a tense kind of symmetry, like a fountain that doesn't entirely agree with gravity. To see why that's unusual, it helps to picture a more typical comet's tail. Imagine Hale-Bopp again, or one of the other bright comets that have graced our skies. In many of those cases, you can see 2 overlapping structures stretching out away from the nucleus. One is primarily dust, heavier grains and particles that get pushed into a graceful, curved tail by the solar wind and the comet's own motion. The other is mostly gas, lighter, more easily ionized particles that respond more directly to the sun's radiation and magnetic fields, often forming a straighter, narrower tail. Dust and gas tails can look different, one broader and more diffuse, the other finer and more sharply defined, but they share a direction. Both of them ultimately point away from the sunday. That's the rule written into the physics of light pressure and flowing plasma. No matter how wild the shapes, the overall message is the same. The sun pushes, and the tails lean back. For 3IATLAS, though, the story is not so simple. This object went from showing almost no obvious tail at all, no long sweeping structure, no classic fan, to suddenly presenting 7 individual jets, some reaching away from the sun, some angled back toward it. It's as if, instead of one big, obedient stream, the comet had turned into a spray of little thrusters, each with its own direction. There is another detail that makes those jets even more curious. 3IATLAS is not hanging motionless in space. It rotates. Observations suggest that it spins roughly once every 16 hours. That means any fixed point on its surface is alternately turned toward and away from the sun over and over, and any gas venting from those points is being swept around in a slow, steady spin. If the jets were just random puffs of gas, emerging here and there without much force, that rotation would tend to smear their traces into a broad, fuzzy blur. Over time, the individual streams would overlap and blend, forming something that looks much closer to a continuous tail. That's what we usually see in comets. Even if there are specific active regions on the surface, the combination of rotation and outflow smooths everything into one main direction of escape. But the jets on 3IATLAS stood out as separate, persistent features, even as the object turned. That suggests they were not weak, momentary puffs, but strong, sustained outflows. Each one was powerful enough and narrow enough to carve its own path into the coma and beyond, keeping its identity despite the slow roll of the nucleus beneath it. The image catches them like frozen fireworks, caught mid-burst around a spinning core. And yet, that elaborate pattern did not last. When astronomers looked again just a day later, in the next clear set of images, 3IATLAS had changed its appearance once more. The delicate spokes of gas, those 7 distinct jets, had blended into a much larger, more unified structure. Instead of many fingers, there was now one giant plume. At first glance, you might be tempted to call it a normal tail. After all, there was now a single, dominant stream of material extending away from the comet, more in line with what people expect when they picture such objects. But the shape, the texture, told a slightly different story. Instead of a long, fan-shaped streak that thinned gently into the void, the main plume coming off 3IATLAS looked more like smoke rising from a fire, thicker near the source, textured, with an almost column-like presence as it moved away from the nucleus. It had the feeling of something vigorously thrown off rather than passively stretched. Measurements suggested that this plume reached nearly 3 million kilometers in length, a structure so enormous it's hard to hold in the mind, and yet it seems to have taken shape over roughly 24 hours. Imagine that. In the span of a single day, a visitor from another star released enough material and with enough energy to paint a plume of gas and dust stretching millions of kilometers across space, visible in the glow of sunlight. It's like watching a single breath turn into a river. And if you look closely at that same image, there is another detail waiting, quieter but no less important, opposite the main plume, extending out in nearly the reverse direction. There is a second, smaller structure, another narrow stream, reaching toward the sun instead of away from it. This second feature is sometimes called an anti-tail, not because it defies the basic physics of light and wind, but because, from our vantage point, it appears to lean in the wrong direction. For 3IATLAS, this anti-tail is shorter than the main plume, measuring at around 1 million kilometers in length, but it is unmistakably there, pointing sunward while its larger sibling reaches away. You might remember that this isn't the first time 3IATLAS has grown a tail that seems to defy the usual rules. Back in the summer, when it was still far out between the orbits of Mars and Jupiter, one of the earliest oddities anyone noticed was a sun-facing emission, an anti-tail. For most comets, that kind of structure is already strange. Tails almost always lean away from the sun, not toward it. Seeing any kind of steady, sunward feature is like watching smoke from a campfire curl down toward the flames instead of drifting into the sky. At that time, though, 3IATLAS was still in the colder, more distant reaches of the solar system. The sunlight falling on it was weaker, the warmth faint. The energy it received from the sun was enough to wake it a little, enough to stir a modest coma and a subtle anti-tail, but not yet the fierce, blazing environment of the inner system. Even then, that sun-facing structure caught astronomers' attention. It hinted that this was not a shy, quiet object, but one with a tendency to behave in unusual ways even before the real heat began. To understand why that matters, it helps to remember what the sun sends out into space. It doesn't just bathe the planets in white light and warmth. It also emits a constant flow of charged particles, electrons and protons, streaming outward in every direction. Layered on top of that are all kinds of radiation, X-rays, ultraviolet light, and more gentle forms as well. Taken together, this outflow behaves like a wind, blowing away from the sun and washing over everything in its path. We call it the solar wind, and much of a comet's tail is shaped by that invisible breeze. When a typical comet nears the sun, its ices vaporize, and the gas and dust are carried outward, Light pushes on tiny dust grains. The solar wind grabs charged particles and sweeps them into long, elegant strands that point away from the sunday. That's why, no matter which way a comet is traveling along its orbit, its main tail always leans back from the star, like hair blown away from a face. It's a simple, reliable pattern, written into the physics of light and plasma. Now, compare that to what 3I-ATLAS is doing. It's no longer out between Mars and Jupiter. It's in the inner solar system, passing near its closest distance to the Sun, where the light is stronger, the heat more intense, the solar wind more forceful. In this environment, you would expect a normal comet to produce a bright, sweeping tail, flowing cleanly away from the star. Instead, 3I-ATLAS is managing to sustain a relatively large, structured, sun-facing plume, an anti-tail right in the heart of that powerful flow. It's as though, in the very region where everything is supposed to be pushed one way, part of this object's outflow is persistently pointing the other. That doesn't mean it's violating the laws of physics, perspective, geometry, and the complex interactions between dust, gas, and gravity can all play tricks on how a tail appears from a distance. But even with those factors in mind, the size and clarity of that sunward structure, especially so close to the Sun, are not what we would call typical comet behavior. Add to that the sheer scale of what 3I-ATLAS has already thrown into space. Those plumes, one stretching nearly 3 million kilometers away from the Sun, another about 1 million kilometers in the opposite direction, represent an enormous amount of gas and dust lost in a relatively short time. For many comets, that kind of violent outgassing, especially near perihelion, can be the beginning of the end. The pressure of escaping material, combined with thermal stress and tidal forces, can tear them apart. Some vanish into diffuse clouds of debris, never to reform as a single body. But 3I-ATLAS, despite all this, appears to be holding together. It has shed multi-million kilometer curtains of material and yet remains a coherent object, not a shredded ruin. That resilience tells us something important. Whatever lies at the heart of that coma is not fragile. It is massive and robust enough to withstand forces that would easily break smaller, weaker comets. There's been a lot of quiet debate about just how big the solid body inside that glowing cloud really is. When you look at a comet, you mostly see the coma and tail, not the nucleus itself, so estimates have to be teased out of brightness and behavior. On the conservative side, some calculations suggest that the central object might be no more than about 5 kilometers wide, perhaps even a bit less. In that scenario, 3I-ATLAS would already be a respectable size, but not outrageously large by comet standards. Other estimates, though, based on the amount of material it is capable of releasing and still staying intact, point towards something closer to 10 kilometers across. Given what we've seen, the powerful outgassing, the strong non-gravitational acceleration, the fact that it hasn't simply crumbled this larger value feels more likely. A 10-kilometer wide nucleus would carry a lot of mass and a lot of internal strength, enough to tolerate the stresses of perihelion better than a smaller, more fragile body. If that is true, it puts 3I-ATLAS in a very special category. Compared to Oumuamua, the first interstellar object we discovered passing through our neighborhood, a 10-kilometer wide 3I-ATLAS would be roughly 20 times larger. Even compared to 2I, Borisov, the second known interstellar visitor, which was already on the big side of what we expected such objects to be, 3I-ATLAS would be about 10 times larger. It is, in that sense, an outlier among outliers, a giant among a class of already rare wanderers. That size matters when you think about where 3IATLAS has come from. Interstellar space is not truly empty. It's filled with dust, gas, radiation, and the occasional larger object. Over billions of years, anything wandering freely between stars runs the risk of being chipped away, cratered, or shattered by collisions. Small objects have a better chance of slipping through the gaps, like fine sand falling between pebbles. Larger ones present a bigger target. The more volume you have, the easier it is to be struck, eroded, or pulled apart. So when we picture a 10-kilometer wide body surviving a journey that might have lasted billions and billions of years, traveling from whatever system first formed it all the way to ours, it's a little like picturing a large, ancient ship making it across a stormy ocean without sinking, long after most vessels of its kind have gone to pieces. It's not impossible, but it's not something you'd expect to see very often. Then there is the timing. Even if you accept that such a large object somehow endured the hazards of interstellar space, it had to pass through our sun's neighborhood at just the right moment for us to notice. For most of human history, even if something like 3IATLAS had come by, we would not have had the tools to recognize what it was. The sky would have held a strange, moving point of light, and then it would have gone again, unrecorded or misunderstood. But this one arrived now, during a brief flicker in our species' story, when we have telescopes on the ground, observatories in space, and spacecraft scattered all over the solar system. We have the ability not only to watch it as a speck, but to analyze its light, map its path, and glimpse its changing form in detail. The odds of all those conditions lining up, the size, the survival, the trajectory, the technology, are small enough that 1 in a million doesn't feel like an exaggeration. It feels like a soft way of saying, this is extraordinarily lucky. So no matter what 3IATLAS turns out to be in the end, a natural rock wrapped in exotic ices, a comet with an unusual composition, something stranger still, it is, without question, a special object. It's the kind of visitor that makes scientists lean in a little closer to their screens, the kind that turns long, quiet data streams into something that feels like a story unfolding in real time. At NASA and in observatories around the world, teams have been following this object for months. Spacecraft orbiting different planets have adjusted their gaze to catch it when they can, each from its own vantage point, from near Earth, from Mars, from elsewhere, along the Sun's family of worlds. They collect images, measure brightness, track changes in color and motion, and send all of that information back in thin, patient streams of data. On the receiving end, those streams wait in servers and notebooks, ready to be untangled. Turning that raw data into understanding is neither quick nor simple. Each instrument sees only a piece of the puzzle, filtered through its own limitations and strengths. Astronomers have to align those pieces, correct for perspective, account for the way light and gas behave, and test different models of composition and structure. It's a bit like trying to understand a person's life from a handful of brief, scattered conversations. There is a story in there, but it takes time and care to hear it clearly. As all of that careful work continues, we're fortunate to have another moment of closeness coming up. On December 19th, 3IATLAS will pass at its nearest distance to Earth. It won't be close in the way the Moon is close, or even in the way some near-Earth asteroids are, but on a cosmic scale, it will be near enough for our best instruments to take another long, deep look. When that day comes, the most powerful telescopes we have on mountaintops, in deserts, above the clouds in orbit, will turn toward this visitor once again. They'll watch how its coma has evolved since perihelion, how its tails and plumes have changed, whether its non-gravitational acceleration is still as strong or has quieted down. They'll examine its spectrum in even finer detail, hunting for the fingerprints of particular gases, the traces of dust and molecules that might explain its strange colors. No one can say exactly what they'll find. It might be that the new observations gently confirm a natural, if exotic, cometary explanation, layers of unfamiliar ice, complex chemistry, and unusual geometry, all working together to produce the behaviors we've seen. It might be that something in the data refuses to fit neatly, leaving the mystery partly intact, a question we carry forward into the future. Whatever the outcome, the approach of December 19th feels like another quiet turning point in this story. A rare, massive object from another star has flown past our sun during one of its most active moods, changed its light and motion in ways that tug at our curiosity, and now drifts close enough for us to study, with almost everything we've built to look outward. For a moment, our paths overlap. Somewhere, teams will be awake through the night, watching numbers update on their screens, checking and rechecking plots and images. Somewhere else, someone will step outside, look up at an ordinary patch of sky, and have no idea that, hidden in that darkness, an interstellar traveler is passing by, carrying secrets from a place we have never seen. And in the middle of all that, between the bright machinery of science and the quiet of an ordinary evening, there is a simple, gentle truth. Whatever 3IATLAS turns out to be, we were here to notice it. We watched it flare and change and curve through our night, and for a brief time in the long history of the universe, we wondered about it together.